similar to a product. If we have a product, our function is a product. If our function is a quotient, something over something else, there's a little more to it than doing derivative over derivative. Unfortunately, yeah, we've got y equals f over g. The derivative is not f prime divided by g prime, okay? So I'm emphasizing that, so hopefully you'll catch on to that. So how does this work? How am I going to do that? Since unfortunately it's not as simple as we would hope. Well, let me actually kind of use the product rule to develop this quotient rule. All right, so we've got y equals f divided by g. If I multiply both sides by g here, that'll get g times y equals f. Okay? Well, now, the goal is I'm trying to find y prime, so let's do the derivative here of both sides. Doing the same thing both sides, that's usually a lever maneuver, isn't it? All right, well, what's the derivative of this side? What have I got? Product? I can use the product rule here. So g prime times y. So I did the derivative of g times the y, and then alternate that to g times the derivative of y, g times y prime. And then, of course, this side just f prime. Okay, so our goal was solve for y prime. I want a y prime. So we're going to try to get y prime on the side by itself. So I'm going to subtract the g prime y from both sides. So that's gy prime equals, and I'll get rid of that, f prime minus g prime y. And let's go ahead and change now. Y is f over g, so let's change that to f over g, back to f over g. Right? Y is f over g, so I can change that back. Okay, and then divide by g, but here's what I'm going to do to kind of simplify things, get it to where the form really that we want. Let me multiply both sides by g next. So that'll make it g squared y prime equals, so I distribute, so it'll be f prime times g, or let's write it g times f prime. And then this times this, well that's kind of the whole reason multiplying by g, because then the g's cancel there, and so it'll be g prime f, let's write that as f times minus f times g prime. So if you got that, what I'm just doing here is I'm solving for y prime, so I'm going to divide by g squared. So y prime is going to be g times f prime minus f times g prime over g squared. That's the derivative. Yeah, it doesn't exactly roll off the tongue there, but here's the way, you know, if you kind of break it down, I mean, you can come up with your own. Some people just say, oh, I'll just remember that. But if I think, so here's our quotient rule. That's our quotient rule for derivatives. For y equals f over g, the derivative is y prime equals g times f prime minus f times g prime over g squared. Here's one way, maybe. This is the way I remember it, okay? If we think of f and g as high and low, so f is high, g is low. The high function and the low function. what have I got? Low times the derivative of high, low d high. Minus f is high, d low. Over g is low, so we got low squared. That's how I remember it. I mean, there's other little twists to that or other little catchy things, but that's how I remember it. Low d high minus high d low over low squared.
The moment you said low and high, that little giggle popped in my head from high school.
Oh, it did?
Yeah.
You did the same thing?
Yeah.
You talked about that before? Yeah, it's just a little catchy way, because it isn't, like I said, it's not something that, oh yeah, that makes sense. No, it's what it is, but it's not just an automatic thing. So that's how I remember it. You know, if you come up with your own way to remember it, then more power to you there. Okay, that's what it is. That's our quotient rule. We have to do this process. Now, if you think about it, it's kind of like our product rule in that, look at the top. The top, you're alternating the derivatives, aren't you? Now, there's the extra thing that you've got a minus, so you got to remember which one's behind the minus, and that's, you know, low d high, you start low. Okay, that's what I remember. Start low. Low d high minus high d low. Okay, so all that being said then, what do we got over here? So we're back to y equals 3x minus 4 over x minus 2. So the derivative is that. This is f, this is g, high, low, however you want to remember it. So I start with the g, right? Low, so x minus 2, not the derivative, just the low. Times then the derivative of the high, or derivative of f. So that's the derivative of f is 3. Minus, reverse that, do the high, or f, 3x minus 4. Times the derivative of the low, or g, which the derivative of g is just 1. And then that's all over whatever g is, or low, squared. It's a little complicated, but I think usually we get used to it. Once we do 1 or 2 or 100, something like that. Now, these do simplify, so yeah, we do want to simplify them. See, 3x minus 6, so you got to distribute your 3 back here. Here, 1, so it's not really there, but anything there, but you do have to distribute the minus. It is minus 3x plus 4 minus 1 times those over x minus 2 squared. And so that gets us, sometimes good things happen, 3x minus 3x, those go out, so it's just negative 2 on top, isn't it? It's negative 6 plus 4 over x minus 2 squared. It's our first foray into that. Okay, so it's not the easiest thing, this quotient rule, but it is what it is. Okay. Now this next one, say we've got this f of x equals ax squared over bx plus c. What is our derivative right there? Okay, so this one again, got our quotient rule coming in, kicking in. However, this one also has something else we haven't mentioned quite yet. I don't think it's come up yet. But notice here I've got a function of x, but I've got a, b, and c also, kind of looking like variables. Well, the rule of thumb that this book and other places use is, yeah, if we've got a function of x or t or something like that, The other variables are playing the role of constants. And so A, B, and C here are constants. Meaning, those are just numbers. So if you see A, B, C, D, maybe throw D or E in there, I guess the first letters of the alphabet kind of thing. That's, generally speaking, those will be your constants. Kind of like quadratic formula, A, B, C. Those are constants in your quadratic equation. Same idea. So if we see A, B, and C, those are just constants. Why do I mention that? Because that'll come into play when we do our derivatives of those things. All right. So, we've got to use our quotient rule. Low D high minus high D low over low squared, or however you prefer to remember that. All right, so low and high, F and G, however. So what goes first? We start with G, right? Low, Bx plus C, times, all right, so here's where that fact A, B, and C are constants comes in, because that is A times X squared, but that's just a number times X squared. It's like 5X squared, or 10X squared, or negative something X squared. A is just a number. What I'm telling you there is you don't have to use product rule on that, because A is just a number. So what is the derivative of, because low D high, so I need to do the derivative of the high. Well, if that's just a number, we just bring down the 2 and multiply it by the A, so it's 2A. And then the new power of X is X to the first, right? 2AX is the derivative of the high. All right, then I do the high, AX squared, times the derivative of the low, so the derivative of the low, Bx plus C, the derivative of that. Well, B and C are constants. So B is just a number, so I'll just have a number times X, so bring down the power, 1 times B, new power is 0, so that's just B, isn't it? And then plus C, so the derivative is C, C is a constant, so the derivative is 0. Yeah, the derivative of the bottom is just B. And then what goes on the down here, downside, well, it's just low squared, Bx plus C squared. And then we're going to simplify that. I think it does simplify a little bit. Is that okay? Question? All right with that? So again, to simplify this, just got to distribute here. So that would be 2 bx times 2ax, so that would be 2abx squared minus, plus 2ax times c, so that's just 2acx. They would usually write the x term last, x part last. And then I have this, again, usually write the x part last, so it'll be abx squared minus abx squared. And then just look to see if there's anything we can combine, which there is, right? Because this and this are abx squared, so those are like terms, if you want to call it that. That's a minus 1, so 2 minus a 1, so that's just going to be 1 abx squared, or just abx squared, plus 2acx divided by bx plus c squared. That's my derivative. Nothing more can be done there. Okay? Now, one other quick point here on this one. Y equals x to the 7th plus x cubed divided by x squared. Okay? Quotient rule would work with that, but I think you'd agree with me. If I don't have to use a quotient rule, that's a good thing, isn't it? So my point on this is, yes, I could use the quotient rule on this, but it's not necessary here, because this one is one that we can do without the quotient rule. We did this one before we did that quotient rule, or one like this before we did the quotient rule. If I go ahead and say, well, let's divide those up by x squared, what I've got for y is x to the 5th plus x, right? Subtracting the exponents. And so y prime here is 5x to the 4th plus 1. The derivative, I don't have to use the quotient rule on that, see? So see what I'm saying? If you don't have to use the quotient rule, that's preferred. We could get there with the quotient rule. We could. But it would probably take us a few more steps than that. So be aware of that. This one and the other one like I did, those are ones where I have to use the quotient rule at some point or another. So we can't get around. But if we can get around using the quotient rule, I say we do that. It's advisable. Okay. Well, let's talk about next here. Let's call it higher derivatives. Yeah, turns out that we don't have to stop at just doing a derivative. We can do a derivative of a derivative. You know, if you think about it, when we were graphing, we had graph of f here. Let me just explain it this way. All right, so we've got something like that. All right, so that's f. Well, f prime looks like this. We've got a 0, 0, we'll do it real quick here. So that's our horizontal tangents, and then positive, negative, positive. All right, so we'll get another graph here. Well, the derivative, how we get those? Those are the slopes of the tangents, right? That's how I got that. Positive slopes. Those are 0 slopes here and here. These were positive slopes. They're up here. These are negative slopes. They're down here. These are back to positive slopes. Okay. All right. Well, doesn't this one have slopes of tangent lines too? Yeah, there's slopes of tangent lines here. So my point is, these derivatives have derivatives of themselves. So we can do derivatives of derivatives because they have, not only do the function have slopes of tangent lines, but we also have slopes of tangent lines of the derivative. So there's derivatives of derivatives. That's our next step, okay? We're not going to graph these. I'm just using that for illustration purposes. These have derivatives because they have slopes of tangent lines. Okay, well, the good news is let's just, easy enough, I think, to illustrate it here. All right, so if f of x equals x cubed plus 2x squared minus 7x plus 4, the derivative is 3x squared plus 4x minus 7. Zero derivative there. Well, we can utilize then the same process and get the derivative of the derivative. And as far as getting it, it's going to be fairly simple because it's just an addition and subtraction there. The derivative of the derivative, well, we call that the second derivative for obvious reasons. Because this is the first derivative now, we'll call it. So now we do the second derivative, and we'll just add another mark there. Double prime is going to be our second derivative. All makes sense, right? So the second derivative is, Well, it's just the derivative of the first derivative, so it'd be 6x for that one, plus 4. 0 derivative there, so second derivative is 6x plus 4. Not much to it. We'll talk about more meaning of it when we talk about a few applications, but as far as getting it, you're just doing, to get the second derivative, you're just doing the derivative of the first derivative. Well, guess what? Third derivative, we can do the third derivative. And it would be 3 marks. Well, the third derivative is just the derivative of the second derivative, which is very easy. What's the derivative of the second derivative here? 6. You know, one like that, you eventually run out of stuff, okay? The fourth derivative would be 0, so the fifth derivative would be 0, sixth derivative. So sometimes they degenerate, but sometimes they, you know, they can just keep expanding or can just keep going infinitely. But anyway, I think you get the idea. It's just the derivative of the first derivative. The one thing, if I go back, let me go back to one we did on quotient rule. Let me, 'cause I think they have you do a second derivative of one like that. Let me just show you here. I got it. Well, I guess I could do some notation here. And do that. So yeah, second derivative. We have double prime of x. You also see it with the Leibniz, kind of strange looking. I don't know that we'll have to deal with it, but just in case, you see it that way. D squared f of x. Just so you know, after the fourth derivative, here's the one they kind of use. It's it looks like a power, but it's in parentheses. So if you see, it looks like a power, but it's in parentheses. That's typically means your second derivative, and that's we usually use that for second derivative, but for fourth derivative, fifth derivative, you'll see it more like this. So just FYI. All right, but the one I was going to show you, y equals, what was it, 3x plus 4 over x minus 2. So the first derivative, go through it real quick again here. Low, d high, minus high, d low, over low squared. So we get 3x minus 6 minus 3x minus 4, negative 2 over x minus 2 squared. Okay, this is first derivative. What about the second derivative? Well, the second derivative is just the derivative of the first derivative, and so, yeah, if you got a quotient, it does get a little more complicated. Let me do, and I guess there's a couple ways we can do it here, but let me do it via the quotient rule again. All right. First of all, remember, we are going to have to take the derivative of the low, right? That's part of the quotient rule. Low d high minus high d low. Well, we haven't learned another way yet to do this. So right now, the way I would do the derivative of that is just go ahead and expand that out. So if I've got x minus 2, let me think of that as, for purposes of getting the derivative and other things, let me go ahead and multiply that out. What was it, x squared, you'd have minus 2x would be minus 4x plus 4. Yeah. So that's how I would treat that one if we come across. I think there is one homework like that. So just go ahead and multiply that out. And then do our quotient rule. So it's low x squared minus 4x plus 4 times the derivative of the high. Well, the high is just a constant, so that's just 0. Minus high, negative 2, times the derivative of the low. So that's where multiplying that out comes in handy. 2x minus 4 over low squared. Well, the good thing about this is that's just 0 times all that, so that's just 0. So all we wind up with on top is be positive 2 times, so it'll be 4x minus 8. Which is a pretty good answer, but you're probably going to ask, how did they get the answer in the back? Because this does simplify. First of all, that factors. You factor off of 4. And then second of all, now, I'm going to go back to factored form of this. The factored form of that is x minus 2 squared. So I've got x minus 2 squared in parentheses here. And that's going to be squared again. So really on the bottom, what have I got? X minus 2 to the 4th. With me there? Well, okay. Pretty good answer, but what do you see? We got a common factor of x minus 2. I can cancel this x minus 2 with one of these, so it'll make me a cube. So I have 4 over x minus 2 cubed. And there's other ways to get that answer, but just wanted to, that's the second